Hello, my name is Doko from Samsung Electronics. I'm very happy to present in SDC 2020. The title of my presentation is Next Gen Embedded Fabric Reference System. In May this year, Samsung announced open storage platform called Project Poseidon in Open Compute project. Project Poseidon is the name of storage reference platform which can implement Embedded Fabric storage system. It is not only software reference, but also contains hardware reference architecture. Today, I'd like to share the details of Embedded Fabric reference system announced in Open Compute project. And we have one more speaker today. His name is Jung-soo, also from Samsung Electronics. I will explain the software part and Jung's gonna touch hardware part respectively. Today, first we'd like to talk what's an advantage of Embedded Fabric and why do we develop Embedded Fabric system, especially targeting open source. Then we wanna explain software solution and hardware system design in detail, and we will conclude and share our future roadmaps. Firstly, I'd like to introduce Embedded Fabric Interface briefly. Embedded Fabric Interface has emerged to break through the scalar limitations of PCI-attached NVMe, which is limited to scale only few hundreds of drives. To overcome this limitation, Embedded Fabric uses a transport protocol over the network to access remote NVMe drives. Through encapsulation and decapsulation, Embedded Fabric can maintain end-to-end NVMe semantics across a range of topologies. In this figure, NVMe command from host side is encapsulated and is sent to the storage server via network protocol. When command is reached to the storage server, it is decapsulated to NVMe command and is issued to local NVMe storage in storage server. Since Embedded Fabric interface eliminates unnecessary protocol translations, it can retain NVMe efficiency and performance over network fabrics. So, why do we need Embedded Fabric system, especially reference system for all? Here are 4 reasons we think. Firstly, NVMe ecosystem is expanding rapidly. According to IDC, NVMe crossed 61.4% share by this year in enterprise storage. And secondly, storage disaggregation has become major trend in data center since mid of 2010. Storage disaggregation allows separate storage resource from compute resource within a server, and thus it can scale storage resources independently in a cost-effective and flexible manner. As disaggregation for NVMe storage, Embedded Fabric becomes more important. Third one is next generation storage brings strict requirements. For example, PCIe Gen4 and Gen5 and high-speed CXL interconnect, NAND-friendly SSD form factor such as E1.X or X3.X. These bring strict requirements such as more power, higher density, higher throughput, finer QoS control, and so on. But although the importance of Embedded Fabric system becomes increasing, as far as we know, there is only few off-source reference system for Embedded Fabric. So, in order to leverage Embedded Fabric ecosystem, we decide to develop both hardware and software reference for Embedded Fabric. Let's move on the subtest solution. Before sharing the details of our subtest solution, I'd like to talk the prerequisite for NVMe Fabric reference system. This helps in understanding the concept and design of our solution. These are 4 prerequisites we think. I'm gonna talk each prerequisite one by one. First prerequisite we think is reference system is able to abstract logical volumes from physical devices. Instead of directly exposing physical device to the initiator, it should be able to make physical device invisible to the initiators, so that we can easily add storage intelligence features like volume management, RAID, compression, tiering to storage solution. But it occurs the necessity of internal metadata management for dynamic mapping. In this presentation, I will talk about the efficient way to manage internal metadata in our reference system as well. Second one is NVMe Fabric reference system is able to support various types of network protocols. Currently, NVMe over RDMA, FC, and TCP are verified. Among them, we choose NVMe TCP by default. Since TCP/IP is already spread all the data center can utilize their existing TCP/IP network with NVMe TCP. TCP is slower than both RDMA and FC, but it can offer reasonable latencies. And recently, SmartNIC, which offers NVMe TCP operator functionality, has been emerging. With SmartNIC, we can shorten latency with lower costs. And reference system can provide flexible NVMe subsystem. In this figure, NVMe Fabric target represents our reference system. It can create one or more NVMe subsystems. One NVMe subsystem consists of one or more NVMe controllers, one and more namespaces, and one and more ports. One of our design decisions regarding NVMe subsystem is to map one logical volume to single namespace in NVMe subsystem. This allows that one NVMe subsystem can have multiple namespaces and thus can have multiple controllers. Suppose that if one NVMe subsystem represents one single volume, then NVMe subsystem is restricted to have only one NVMe controller and one namespace. So, provide flexible NVMe subsystem will decide to map one logical volume to single namespace. The relation of NVMe Fabric target, NVMe subsystem, namespace, volume is 1 to n to m to m, which means one NVMe Fabric target can have multiple NVMe subsystems, and one NVMe subsystem can have multiple namespaces, and one namespace is mapped to one logical volume. The next and last prerequisite for software solution is it should be able to fully utilize the performance of NVMe SSD. That's quite natural. This graph shows the relative performance between sequential and random in case of reads and writes. As you can see, sequential performance of NVMe SSD is much faster than random one, both reads and writes. The next graph shows the relative performance between clean states and sustain of NVMe SSD. You can see that clean state performance in writes is faster than sustained performance 3 times more. This gives us an insight that the reference system is better to sequentialize user IOs to provide more performance, especially in case of writes. It is important to should be able to keep SSD as clean state as much as possible. Also, it is necessary to understand the characteristics and limitations of NAND flash. As you know, NAND flash has several limitations such as different program and erase unit and not allowed in-place updates, and need EPI and read reclaim to keep data safety. If reference system is aware of these limitations and is synchronized with current state of NVMe SSDs, then it can have a potential to provide more performance and more stable QoS, which can let satisfy strict requirements of next generation storage. Let me explain the concept of our software solution. To exploit the performance of NVMe SSDs, we allowed our software to run as user application, not run in kernel mode. For this, we adapt user space drives to manage NVMe SSDs and NIC for NVMe Fabric. And we've decided that our software solution can abstract logical volumes from physical devices. It can provide customized virtual devices to the initiator via NVMe Fabric interface. User can select the customized option when creating virtual device, such as its capacity and throttled performance, and applied storage features like RAID type and more. Now, let me move on the software stack of our reference system. Our reference system consists of 3 layers such as storage resource management layer, metadata layer, and user data layer, conceptually from bottom to top. We built each layer from the perspective of providing both NVMe Fabric connectivity and storage system functionality. So, you can think of each layer is very intuitive. Storage resource management layer is literally in charge of managing and monitoring storage resource for NVMe Fabric target, including NVDIMM and SSDs. And it provides an environment of executing the modules from upper layers. Metadata layer is responsible for guaranteeing and seed of internal metadata. For this, it provides simplified interface to other modules. Also, it has journaling functionality to efficiently store the updated metadata. And user data is in charge of handling user I/O and provide NVMe Fabric connectivity. And it is optimized for providing higher performance and stable QoS. I'd like to share 2 characteristics of our software solution. These characteristics are closely related to our design decisions. First characteristic is that our software solution adapts user space NVMe Fabric and NVMe I/O mentioned in previous slide. With user space drive, user application can directly issue I/O to NVMe device. So it can avoid overhead of system calls and data copies. As a result, it can allow to spend more CPU cycles for storage service, and thus can even enable better latency and IOPS. Second characteristic is our reference solution adapts write buffer to make SSD friendly. The brief write sequence using write buffer is shown in this figure. All user data or user writes are first stored in the write buffer and then flush them to NVMe SSD in low structured manner when write buffer is full. If write buffer is placed in non-volatile memory, user data in write buffer is guaranteed persistency. Thus, it can shorten write latency to provide stable QoS. Also, write buffer easily sequentialized user writes. We can enjoy the sequential write performance of NVMe SSDs, which is 3 times higher than random performance. And on the low structured write strategy, you can easily make SSD to clean state using trim command to all data. This is brief IO stack of software solution. It consists of 2 parts, front end and back end. Front end is optimized for minimizing latency of user I/O, while back end is optimized for maximizing throughput among multiple SSDs. Only mandatory jobs for user I/O through NVMe Fabric interface performed in front end. Except for these, all other jobs like RAID, flush, GC are performed in back end. Front end exploit dedicated thread model and directly interact device to minimize latency and make QoS stable. Compared to front end, back end adapts thread pool model and interact device indirectly and offers it to front end thread. Let me explain the challenges and our detailed approaches to overcome the challenges. To be honest, we've met a lot of important challenges during the system implementations. But due to the time limits, I'd like to touch the challenges related to performance and QoS only. First challenge is how to saturate high-speed network such as 100 gigabit or 200 gigabit network via TCP. Basically, our approach is to follow SPDK philosophy. But even if we use SPDK, CPU is still bottleneck, especially it's harsh with small I/O. Since TCP stack consumes more CPU cycles compared to RDMA and FC, it makes worse. These figures are flame graph of NVMe over RDMA and NVMe over TCP in case of writes. As you can see, TCP stack consumes 3 times more CPU resources than RDMA. Actually, these results are measured in PCIe Gen3 based CPU, but in PCIe Gen4 environments, which doubles up the performance of SSD and network, we believe that CPU bottleneck would be much worse. To solve the CPU problem, our software solution supports NUMA availability and separates CPU circuits for front and back end. This allows to minimize UPI transactions and spend more CPU cycles for storage service. For front-end thread, CPU affinity is setting NUMA 0, and back-end threads are running on different NUMA. But even if our software solution separates front and back-end jobs, remote SSD access is inevitable because it maintains multiple SSDs as one big array. This figure shows the relative performance between local SSD access and remote SSD access. As you can see, the remote SSD access has 10% overhead compared to local access. So, it would be better to minimize remote SSD access. And in order to eliminate lock contention and easily scale to multiple threads, we adapt a per thread structure for everything. For this, we use thread local storage and per thread queue pair for NVMe SSDs, and so on. In this figure, as you can see, each thread has its own resource such as IOAT and queue pair for NVMe, so that it can easily scale. However, in storage system, some jobs or some data should be shared. So, as a second best solution, we used lightweight synchronization like RW log or atomic variable instead of mutex. I'd like to move on next challenge. According to our observation, Initiator SW Stack does matter to fully exploit environment fabric performance. Fortunately, in case of reads, both kernel and user space drives can achieve max performance. But in case of writes, only user space drives can meet max performance. In this figure, you can see that user space driver of Initiator side provide 30% more bandwidth and 50% lower latency compared to kernel drive in case of writes. Third one is how to manage internal metadata efficiently. To maintain various types of internal metadata for storage system like mapping table, bitmap, journaling data, which have different write pattern and write granularity. User space file system is necessary to leverage user space drivers. But in order to guarantee asset of metadata, minimum one more writes for journaling is required, which may hurt throughput and QoS of user writes. To minimize this overhead, we built independent I/O paths for metadata writes from user I/O. Also, we exploit user space RAM disk with IOAT. And we provide specific file interface to other modules like append-only file to make software stack simple by forcing behaviors. The fourth and last challenge is how to provide fault tolerance when NVMe drive fails. Since hardware RAID card for NVMe SSDs does not become popular yet, so it is necessary to support software RAID or eraser coding for providing fault tolerance. We choose log structured RAID approach because we stored user data to SSDs in log structured manner, so log structured RAID follows naturally. The brief file sequence of log structured RAID shown in this figure. All user writes are first stored in write buffer, and RAID parity is only calculated when write buffer is full, and then flush them with user data in log structured manner. This can reduce WAF and QoS impact for user I/O. Finally, I'd like to share our future works, and I will hand over the presentation to Jung-soo. We are considering that make our software solution more NUMA aware. For this, we have a plan to adapt multiple arrays to only maintain SSD directly connected to single CPU socket. And our reference server is equipped with PCIe Gen4 based CPU. Unfortunately, we haven't been able to measure the performance on that server. So we will share more performance result after measuring on that server. And one more software features will support it. Finally, we will support more end-to-end optimizations. If necessary, we have a plan to modify SSD firmware for our software solution. We will open source Poseidon software at the end of this year, so please stay tuned.
Hi, I'm Jung-soo Kim. I'm taking charge of developing SSD reference system in Samsung Electronics. Today, I'd like to talk about Poseidon hardware system for NVMe Fabric. Firstly, I'd like to talk about the advantage of this aggregate architecture in data center, especially. And I'd like to go over hardware architecture and detailed design decisions of the system. So, NVMe Fabric is a standard protocol for this aggregate architecture. So with the traditional direct attached architecture, you will need many CPUs and SSD drives to build a storage pool in the data center. But by disaggregating CPU resources and storage resources, you can reduce the number of drives that needs to build storage pool in the data center, and you can increase the CPU and SSD utilization. NVMe-oF Fabric is a standard protocol to enable this aggregated architecture in the data center. With the traditional direct attached architecture, you will need many CPUs and SSD drives to build a storage pool. But by disaggregating the compute resources and storage resources, you can increase the CPU and SSD utilization. So if you have this aggregate architecture in your data center, you can reduce the TCO of infrastructure, especially for the storage spending. And since it's the shared network storage, it's more easier to increase and decrease the capacity of storage pool. This aggregate architecture offers more flexibility to the data center. So we believe that storage system is evolving towards the this aggregated manner. So we defined our Poseidon system as open source and high performance and shared network storage system for NVMe Fabric. If you look at the characteristic, it's got an open hardware. We think that if we open the software and hardware design, the ecosystem of NVMe Fabric will be expanded. Since the system is for a shared storage system, it's got to support high bandwidth and low latency, and system should be support high density. Should be high density storage system. And since our target customer of the Poseidon system is data center, general data center customer, the system should provide some level of reliability for data center. Let's go over more details on each item. As I mentioned, by open sourcing the NVMe hardware system, we believe that we can expand NVMe Fabric ecosystem further in the future. So we plan to contribute the hardware design, especially to OCP community Open Compute project end of this year. And that our target customer is a general data center where they use the standard 19-inch rack system. The chassis is designed for the 19-inch standard rack. To enable the high performance, the system should be support high bandwidth, storage, and the network. And the system supports the DDR4 3200, the latest main memory also. And the system should support low latency, and it utilizes NVMe, the latest NVMe SSDs, and it supports the RDMA and TCP offloading to reduce the CPU resources further. And if you want to maximize the performance of the system, you can install MVD modules so that the software can store the metadata and user data to MVD memory. And it's for the shared network storage system, and the system should offer the high density storage and high efficient storage system. With the Poseidon system, there is a 32 NVMe-oF SSDs in one new system, and with the 8 terabyte of a single SSD drive, you can have maximum 256 terabyte of storage capacity in one new system. And we adapted the latest EDSFF Form Factor E1.X SSD to increase the system efficiency further. And it's a storage system, which means the system should provide some level of reliability to the customer. Since our target is general data center, our system provides data center reliability. For example, it supports hot-swappable SSDs and PSU, and it supports the dual port high speed, high bandwidth network controller, and it supports software read and hardware for the SSDs. And it is designed for the NVMe fabric system, and naturally the system utilizes NVMe SSDs and supports NVMe and TCP offloading engines. So this is an overview of our system design. On the front side of the system, there are 32 E1.S NVMe SSDs on the system, and those SSDs are connected to backplane by orthogonal connectors. I'm gonna go over more. I'm gonna talk about more deeper about why we chose the orthogonal connector and horizontal backplane. And there are two PCIe Gen4 100 lane switches on the backplane, and on the middle of the chassis there are 8 40mm dual motor system fans. On the motherboard side, this is a dual socket x86 system. The system used the latest PCIe Gen4 CPUs. And on each CPU, it has 16 DDR4 DIMMs, and you can have total 32 DDR4 main memory on the system. On the rear side, there are two full height half-length PCIe slots. You can install 2 network controller on the PCIe slots. Also, the system supports one more network controller. You can install OCP version 3 network card on the back. So technically, in total, the system can have 3 network controllers. Also, there is some space on the backplane to install NVIDIA power module. This system block diagram shows the PCI topology of the system. So we designed the system PCI topology symmetrically to minimize the socket-to-socket traffic. So if you want to maximize the performance of NVMe fabric system, the software solution should be able to aware the new architecture so that it can reduce the remote SSD access from different side of a CPU. And another reason that we designed the PCI symmetrically is by having symmetrical PCI topology, PCI I/O the system can offer constant performance of I/O. If you look at the downlink side on the yellow box, each SSD is connected to PCI switch by PCIe Gen4 4 lanes. So since every SSD on the system is connected with 4 lanes of PCIe Gen4, you can enjoy full performance of single SSD drives also. So on each PCI switch, the SSD are connected, 16 SSD are connected by 4 lanes, and there are total 64 lanes connected to PCI switch on downlink. If you look at the uplink side of the system, 32 lanes of the PCI, 32 PCI lanes are connected to each CPU, and PCI slot, 16 lanes of PCI slot also are connected to each CPU. On CPU 1, there's another 16 lanes is used for OCP NIC slots. So we have investigated SSD form factor very carefully when we designed the system. So since the EDSFF form factor is designed for data center, it has many benefits compared to the traditional form factor like U.2. There are different kind of E1 form factor, E1.S, E1.L. E1.L, you can have a maximum 32 terabytes of capacity. E1.S, you can have 5 different options, thickness options from 5.9 to 25 millimeter. We found that our data center partner doesn't want to have too much capacity in a single drive, because when a fault SSD when a SSD fails, it takes too much time to rebuild or copy a fault SSD to another one. So Poseidon system supports 9.5, 5.9, and 8.01, and 9.5 millimeter SSDs. As you can see on the table, as the thickness getting thicker, the SSD can have more power as the density, as the thickness, as the SSD getting thinner, you can design the system with more density. And we compared and studied the different thickness of U1.S. So we took summer simulation to decide the right thickness of U1.S SSD for the system. So it turns out that 9.5 millimeter U1.S SSD, which has the enclosure, satisfies the OCP NVMe spec. This is the thermal characteristic of U1.S, 2 different form factor, 5.9 and 9.5. It turns out that 9.5 U1.S SSD meets OCP NVMe SSD spec. If you look at the airflow requirement of OCP spec, the system airflow should be less than 1.5 meter/sec in 35 degrees C ambient temperature. It turned out that 5.9 millimeter SSD couldn't satisfy the requirement. If you utilize 9.5 millimeter to the system, you can increase the system efficiency because the system fan can learn less speed compared to different form factor. Also, the system adapted horizontal backplane with orthogonal connector. If you compare with traditional U.2 U.2 form factor with vertical backplane, you can have more space for air to pass through the system to eliminate airflow impedance. So we simulated the two different type of backplane designs. As you can see on the picture, with the vertical backplane, there are some turbulence on the backside of the SSD. With the horizontal and orthogonal connector, you can see that air flows very smoothly through to the system. So we found that if you adapt the horizontal backplane with orthogonal connector, you can lower the SSD temperature by 1 to 2 degrees C compared to traditional design. In summary, Poseidon system is high bandwidth, low latency, and high density network storage system, and is open source hardware based. It's also PCIe Gen4 based, and we designed the system PCIe topology symmetrically. We also adapted E1.X form factor with horizontal backplane and orthogonal connector to increase the system power, to increase the system power efficiency further. So the system will be released, the POC system will release this October. So we want to verify feasibility of both hardware system and software in real world environment. We are going to run and plan to test performance, reliability, and functionality of the system at the data center. Also, we want to run some benchmark test, like a storage spec or ML-POF. This is the POC system architecture. We will deliver 3 Poseidon systems and 2 initiators each. So there will be 3 initiators total. And each Poseidon system will be connected to dual switch and by 200 gig Ethernet ports. Thank you very much. I'm more than happy to receive any feedback from you. And if you have any further question, feel free to send email to Doko or me. Thank you very much.